So welcome, ladies and gentlemen out there in the Corona pandemic. I hope that you had a good lunch and that you now have an open ear to listen to the latest news in the European district heating and cooling sector. So welcome to this week's DHC Plus talk. Some of you might have participated in previous webinars of this weekly series. For others, it's the first time. In a very informal atmosphere, we want to discuss topics on district heating and cooling and give you inspiration and ideas for your work. So just relax and enjoy. One remark in advance. So if you have any questions to the presentations we will show you, you can ask them by using the question box. So please don't hesitate to use this question box, and we will have our question and answer section later on, where we can address all your topics and concerns. Not the concerns, but also the ideas. So my name is Stefan Holler. I'm a professor for energy technology at Hawk University in Göttingen, in Germany. And I'm Vice Chairman of the DHC Plus Technology Platform. Today, I'm the moderator of this webinar in which we like to honor and celebrate the winners of this year's DHC Plus Student Award. So first, as a tradition of this series, I want to show you my favorite coffee mug. And it's this one here. So this is, it shows the skyline of the city of Mannheim. And that's the city where I started my professional career in the energy sector. And what is special on this mug is the fact that I can illuminate the city when I pour a hot drink in it. I will demonstrate it to you. I hope you can see this. So this is the water tower of the city of Mannheim and the television tower. And you see all the buildings are illuminated. And this always reminds me on how important our work in the energy business is for cities and how energy makes the difference. Before we are going to listen to the short presentations of the awarded research papers, I would like to give you some short background information on the technology platform DHC Plus and our activities in the field of education and training. The technology platform brings together members from all business and research fields of the European district heating sector and focuses its activities in 4 pillars. You can see here the education and training, advocacy and communication, research and business network support, as well as the knowledge hub as an important medium for information on our sector. Today, we are highlighting the pillar education and training. So the DHC Plus Student Award is a prize which is awarded annually since 2013 to appreciate excellent research of young scientists in the field of district heating and cooling. Traditionally, the award ceremony is linked to a conference or any other important event of our sector. And in the picture here, you can see the winners of the previous years and the events where the ceremony has taken place. As you all know, we have not the possibility to meet in presence at the moment. So this year we have chosen this format of an online event for this year's 8th edition. So next, I want to shortly give you an overview on the process of the evaluation and selection of the awarded of the best papers. In total, we received 11 applications from 10 countries. And these papers, in the size of around 8 to 10 pages, they were evaluated according to scientific importance, to the methodology used, creativity, and, which is important for us, the expected market impact. At this point, I would like to thank our jury members, which are representing the academic and the industrial, the business sector. Thank you to all of you, which are named here, who participated in the evaluation process and read all these interesting papers. So now we come to the short presentations of our this year's winners. And we were going to start with the third place, which goes to Martina Kapuna. Martina is from Pescara in Italy, and she lives in Torino for about 7 years. Currently, she is a PhD student at Politecnico di Torino, and she works on district heating network models towards next generation systems. So Martina, can you please switch on your camera now?
Good afternoon. Hi.
Hey, Martina. So how is it going?
Good, thank you.
Okay, so you disclosed us beforehand that you have spent the lockdown with your roommates with cooking and experimenting with new dishes, and you were playing board games. I would like to ask you, what was the role of your favorite coffee mug in the lockdown?
Yeah. Here it is.
Very nice.
It is a tea mug that comes from my childhood, and I still use it because it is funny and it makes me happy. So I love it.
That's good. Very, very nice. Okay, so the floor is yours now for a 12-minute presentation of the results of your work with the title Integrated Demand Side and Production Optimization of Complex District Heating and Cooling Networks.
Okay, can you see my screen? Okay, so you can see my screen?
Yes. Perfect.
Okay, perfect. Let's start. So today I'm going to share with you the results of this work that is about a novel optimization tool applied to district heating and cooling networks and combines together the demand side optimization and the production side optimization. But in order to understand the goal of our analysis, let's start by defining the system that we have considered. It is a small district energy system made up by several users, and these users have predetermined needs in terms of heating, cooling, and electricity, and are connected to a local production plant by means of an electricity network, a cooling network, and a heating network. And so on the wall, we have 3 main interconnected players in our system. These are the users, the networks, and the production plant. And our goal would be to satisfy the daily heat, cooling, and electricity demand of the users by finding the best configuration of the system, which allows to minimize the predefined objective function, that in our case will be the total daily cost. And this will be done by means of a global optimization tool, which takes into account all the main elements of the system. For what concerns the production plant, it is made by multiple components. Here you can see that we have a heat-only boiler, a cogeneration plant, a photovoltaic system, an electric heat pump that can produce both heat and cold, an absorption refrigeration unit, and 3 storages. And the external resources that drive the whole system are natural gas and electricity purchased from the grid. And these are the only resources coming from the external system. So they will be the only terms that are associated to cost and will appear in our objective function. So generally speaking, they are the fluxes that we want to minimize. And as you can see from the scheme, we have also inserted the possibility to sell electricity to the grid if our production exceeds the request. So on the wall, we want to buy the least possible from the external to satisfy the heating load, the cooling load, and the electricity load. But while the cooling load and the electricity load are constant, the heating load is flexible. This means that we can also act on the customer side to optimize our system. And this is what is generally called demand side management, and it's extremely useful to solve some problems, like, for example, the problem of the morning thermal peak, which poses some limits on the full exploitation of high efficiency plants like the cogenerator, and which therefore increases the cost. But let's see more in detail how demand side management works. So basically we have our system, and what we want to do is to modify, is to assume that the buildings have a certain flexibility on their thermal request, and to modify their request in order to modify the heat load at the production plant, and in particular to reduce the peak. But in our case, we suppose that just anticipations up to 30 minutes are possible, and that the energy absorbed by each building during the day is constant, and this is to avoid to affect the user's thermal comfort. And so we want to find the best anticipation of the building that allows us to minimize the peak request. But in order to relate the building request to the heat load of the thermal plant in a proper way, we need to use a model in order to take into account all the relevant thermal dynamics that occur in the system, especially when anticipations are applied. And so the district heating network model that we use is a physical model. It is based on the conservation equations of mass, momentum, and energy. And it uses a pseudodynamic approach, which means that the fluid dynamic problem is treated as a steady state, while the thermal problem is simulated dynamically. We use the graph theory to describe the complex structure of the network and the network topology. And this means that the heat pipe is treated as a branch, and each inlet or outlet section as a node. And finally, the model is applied to both the supply and return lines of the network, so that all the dynamics are properly described. So on the whole, the optimization tool that we propose is composed by three parts. The first part is the demand side management of district heating users, which aims at finding the best set of anticipation of the building. And this is done by means of a genetic algorithm. This genetic algorithm needs to solve at each iteration the district heating network model in order to find, given the set of anticipation, the heat load at the production plant. And this is done by means of the thermofluid dynamics model that we have described. And finally, the genetic algorithm also needs to solve the production optimization, which goal is to determine, given the set of production units, which ones must be switched on and when, in order to minimize the total daily cost. And thanks to the assumption of constant efficiency of the components, this can be done by means of a linear programming algorithm. And this is on the whole the novelty of our approach, which combines together the demand side management of district heating users, the network model, and the production optimization in a unique, comprehensive approach that, how we see, will bring to more powerful results with respect to a sequential approach in which you consider all these parts as separated. But let's see the results. Here we can see the evolution of the heat load at the production plant, and in particular the dashed line is the non-optimized one, so the one without demand side management, while the red line is the optimized one, obtained with optimized set of anticipation. So we assist to a modification of the plant thermal load, which brings to a reduction in the thermal peak that in this case is above 15%. Here we have the result of the production optimization, and we can see in particular how heat, cold, and electricity are produced in the first row and consumed in the second row. For what concerns the heat, we can see that the heat consumption is mainly due to the thermal load, that is the one that we have obtained with the demand side management, so the one that we have seen in the previous slide. Then some other heat is absorbed by the absorption refrigeration unit to produce cold, and finally by the storage. And obviously storage consumption means that the storage is charging, while storage production means that the storage is discharging. Then the heat is produced by the cogenerator and by the heat-only boiler, while the heat pump is just used few times. The cold is almost totally produced by the absorption refrigeration unit, even if the storage is used to shift the production when it is more convenient. That means when heat consumption is more convenient. And finally, the electricity, the electricity is produced by the cogenerator and the photovoltaic when available, while the remaining part is purchased from the grid, and the storage is used to buy from the grid when it is more convenient, so where the electricity price is lower. So we assist to a smart management of the production unit, which brings to a significant cost reduction. These reductions are summarized in this table, and we have a 15% reduction with respect to the base case, which is the one without storage, without production optimization, and without demand-side management. But meaningful results are also obtained with respect to the sole production optimization and the sequential approach. This is the one in which you first reduce the peak and then in a second moment optimize the production. And that's it. In conclusion, we have obtained the tool which brings to promising results. These results can be further enhanced by enlarging the flexibility of the end users. That is to say, for example, if the anticipations greater than 30 minutes are possible, and they can be further enhanced if larger systems are considered. This work also opened up several resource opportunities for future work. First of all, the cooling and electricity loads can also be assumed flexible, but this will require to include also the models for the cooling network and the electricity network in the optimization tool. Also, another point is to increase the number and complexity of production units. Then we also need to study the effect of the introduction of nonlinearities in a model, like the nonlinearities that are due to, for example, nonlinear efficiencies of the plant. And finally, in our work, we have considered all the production units are concentrated in a unique point, when in real cases they can be distributed everywhere along the network. And so also this point should be taken into account. Well, that's it. Thank you for listening. And in a while, I will be happy to answer your questions.
All right. Thank you very much, Martina, for this very good overview of your work. We will not ask the questions right now, but we will collect them for the question and answer section that we will have after all three presentations. So to all of you listening, please send your questions in the question box, and then we can answer them later on in total. So again, thank you very much, Martina Kapuna, and congratulations to the third place. So now we come to the second place winner, which is Antoine Fabre from Mines ParisTech. Congratulations to you, Antoine. Antoine Fabre is a PhD student of Mines ParisTech. He is currently working on a methodology for performance evaluation and optimization of operation strategies on district heating networks. Welcome, Antoine. How are you doing?
I'm well, thank you.
That's fine. So I'm wondering your favorite mug. How was it involved when writing your paper?
Yeah, it's this one. Yeah, so it's a gift from a friend. So I take this mug with me during my last holidays in Nordic country. And during the lockdown, it remembers me the holidays and the good time I spent there. So
okay,
it's pretty nice.
That's good. Nice. Okay, so the floor is for your presentation about now we have the topic of substations. So the topic of your article is substation malfunction detection, indicators. Yeah, it's about indicators to improve the operation of district heating networks.
Oops.
So the floor is yours. We can see the slides and we can hear you perfectly.
Okay, perfect. So good afternoon, everyone. So I will present my work on substation malfunction detection indicators to improve the operation of district heating network. So firstly, a little bit context. So European Union and France have enacted the development of the district heating system through different laws, and with the specific objective for district heating system. So here in the graph, you can see the current situation in France. So you have in green the energy share derived from renewable energy in district heating system. In black, there is the objectives from the law, and in blue, the projection from 2013. And you can see that the target will not be reached in 2014. So there is a need to develop the district heating system in France and also to improve the existing one. And we focus on the second point. And so I wonder how to improve the district heating network performances. The answer is quite simple, is by decreasing the return temperature. But it's easy to say, but not so easy to do. But for example, we can decrease the return temperature by correcting the malfunctions. Indeed, there is a malfunction on district heating system are very common. For example, according to a study on 2 Swedish district heating networks, only 26 of the substations work correctly. So there is a need to work on these malfunctions. Moreover, due to the complexity of the system, the origins of malfunction are numerous, but the most usual one have been detected. So it's damage or manually adjust valves, poor substation control, and also unsuitable secondary system. So in the literature, some performance indicators have been developed. We could mention Zinco in 2005 and Goldenberg in 2014. These indicators are able to detect if there is a malfunction, but they are not able to detect the origin of the malfunction. And in the real world, the operators don't have the time to look for the origin of malfunction. They don't have the tool to correct and detect malfunctions. So my work is on this point. So my objective firstly was to develop a district heating model including the secondary side, because there is a lot of interaction between primary side and secondary side, and a lot of malfunction also on the secondary side. And secondly, it was to assess the impact of usual malfunctions to create performance indicators able to distinguish each of them. So the methodology is the following. Firstly, we study the impact of malfunction on our numerical test bench. After we create performance indicators, then we test them on the numerical test bench, and at the end, we validate the indicator on in-situ data. So today I will only present 2 specific objectives. So the detection of 2 specific malfunctions, so the detection of blocked valves and the detection of full heat exchanger. So when I talk about valves, I talk about the control valves here in the primary side of the substation. These valves control the flow rates passing through the heat exchanger. So that's right. So okay, so first I will give a brief description of my model. So this model has been developed through Modelica di Mola. So it's a physical model. So firstly, you have the production model. So composed of a geothermal heat exchanger and a gas boiler, controlled through a supply temperature law. After you have also the primary network and the pump. The pump is controlled through a pressure law. And after you have a model of a substation and is and the control system, the secondary network and its control system also, and buildings model. So firstly, I will talk about the detection of blocked valves. So on our model, we test the different cases of blocked valves. So 4 cases of valve blocked on different opening degrees, so 10%, 25%, etc. So when we put this malfunction on our model, you can see that with only 10% of the substation with a blocked valve, there is a significant impact on the performance. But also, we see that the valve blockage leads to an instability of the flow rate, as you can see on the figure here. In blue, you have the reference case. You can see there is practically no instability. And in all the cases where there is blocked valve, you can see a lot of instability. So in order to quantify the instability, we decided to do it through the relative mass flow rate variation. So we compare the mass flow rate at 2 consecutive time steps. The time step is about 1 hour. And to evaluate the frequencies of this variation and the difference between all the cases, we decided to do a frequency signal analysis or Fourier analysis. Firstly, we do it on non-blocked valves. So you can see the results here. So you can see that the biggest variation of mass flow rate appears every 24, 12, and 8 hours, with a very low magnitude, just only about 1.6%. So, sorry. So it corresponds to a classical daily operation in buildings. So this behavior is completely logical. And after, we do the same analysis on substation with a blocked valve. And as you can see here on the Fourier analysis, the magnitude of the peaks are higher, and the biggest variation appears for periods inferior to 6 hours, so more than 4 times a day. So nevertheless, this analysis is overly complex to be used on the field by the operators. So we decided to develop an indicator easy to calculate. So this indicator consists in counting the number of time per day when the relative mass flow rate variation is superior to 15%. If the relative mass flow rate variation is superior to 15% more than 4 times a day, there is a regulation issue, so a blocked valve. Here you can see the results from the numerical test. For the reference case in blue, the result is never exceeded, but it does frequently for the case number 3, which corresponds to a valve blocked on 50% of opening. So you can see the time where the result is opening is exceeded by the wait point here. So here the time scale is about 2 days. So you can see that the result is exceeded more than 4 times a day. So there is regulation issue. So in order to validate this indicator, we tested it on in-situ data. So here, the result demonstrates that there is no control issue for the substation X here. So you can see here the time scale is about 1 week. So you can see in red the time where the results are exceeded. So you can see that there is practically no exceeding. But for the substation Y, you can see that the result is exceeded more than 4 times a day, a lot of time. So we can consider that in this substation there is a regulation issue, and this analysis was validated by the operator of the district heating system. So the indicator is working. Next, so the second point was the detection of full heat exchanger. So with no surprise, the fouling impact the performance of the district heating system, but the full heat exchanger also leads to an increase of the heat exchanger's thermal resistance. So in classical substation in France and in Europe, the heat exchanger used in substation are plate heat exchanger and contraflow. So for this type of heat exchangers. The thermal resistance without fouling depends only on mass flow rates, as you can see in this equation. So the thermal resistance depends also on the constant here named gamma. This constant depends only on the dimension of the heat exchanger and the characteristic of the fluid. During the operation of the district heating system, the thermal resistance of the total thermal resistance of the heat exchanger is the thermal resistance without fouling plus a fouling resistance called RF here. And so, after an analysis of our data and simulation, we consider that the fouling downgrades significantly the return temperature, so about 5 degrees, when the ratio between the total resistance and the resistance without fouling is up to 1.4. So we get this type of indicator. So we plot the thermal resistance corrected from a mass flow rate ratio, so corresponding to the last equation. So as expected for the reference case, so without fouling, the evolution of thermal resistance corrected from mass flow rates is linear. So it's a good news. Here, so we plot the results, calculated results, and after the green point, or the case where there is a fouling, very dynamic and fast fouling, and you can see here that the result is exceeded, and an important fouling is detected. So the numerical tests show that the indicator works, but as before, we decided to test it on institute data. So so we looked at a substation, another substation. Here you can see the evolution of thermal resistance in time. So around the 15th of November, the heat exchanger have been cleaned during the maintenance operation, and you can see so a meaningful drop of the thermal resistance. So here, to test the indicator. So here in blue, you have the evolution of thermal resistance after the cleaning. So you can see we are under the results, but before the cleaning, when the fouling was very high, as you can see, the points are beyond this result. So this indicator was able to detect an important fouling here. Yes. So to conclude, so in my study, I have developed a district heating system model, including the operation of the secondary side, all the control, etc. 2 possible malfunctions have been tested, so blocked valve and full heat exchanger. 2 specific indicators have been developed and validated, so the instability of mass flow rates at the primary side, and also the increase of thermal resistance corrected from mass flow rates. So in the following works, I will study other malfunctions, such as unsuitable secondary side or defecting temperature sensor, etc. There is a lot of different malfunctions possible, so there is a lot of work to do. So yes, so thank you for your attention. I'm waiting for your question after all the presentation.
All right, thank you very much, Antoine, for your presentation. This interesting topic, and also it was only a short insight, and there are a lot of more details in your research. But as for Martina, we can answer questions a little bit later. So thank you again for now. And we now come to the winner of the 2020 District Heating and Cooling Student Award. The first place winner is Benedict Leitner from Austria. And Benedict is living in Vienna. He's currently at the end of his PhD thesis at the AIT, which is the Austrian Institute of Technology. And hi, Benedict. He's doing this PhD thesis in cooperation with the Technical University of Vienna. Benedict has a background in technical physics and economics, and what is very honorable, you are currently in paternity leave, as I learned, and you're
yes.
on a bicycle trip in Austria. Is that correct?
Exactly. Yes.
Wow. So that's great. So he told us beforehand that he's currently cycling through Austria on a European bicycle path.
I took my 1-year-old son, so if anyone wonders.
Okay, so you are somewhere on your trip at the moment, and so thank you very much for joining us here today and sharing your results of your work. So no real holiday, but the mind is always on the topic and on the research. My question first: your favorite coffee mug, is it with you on the trip?
I have my favorite coffee mug for traveling, so it's really lightweight. It accompanied me already on several trips, so I brought it with me also for this trip.
Very good. Okay, thank you. So the floor is yours now for presenting the results of your work. The title of the paper is Simulating Smart Coupled District Heating and Electrical Distribution Networks, another important topic for our future of the sector. So the floor is yours, Benedict.
Thank you. Yeah, as already mentioned, I will talk about integrated or sector-coupled networks with a focus on district energy and electrical distribution networks. So the motivation for this is that both heat and power networks are rapidly transforming from centralized and often fossil fuel-based generation to distributed generation storages, integration of prosumers, widespread use of intelligent control, low energy buildings, and also an increased integration between the sectors. So basically this complexity of multi-domain systems often requires to assess in detail how these multi-energy use cases affect the system, and we also need means to test smart control algorithms before they roll out in the field, basically. When I started my PhD, no real method to assess electric distribution networks, district heating networks, together with advanced control systems existed for timescales of several seconds to hours, days, or even years. So this was basically the motivation for me to try to develop some method that allows me to study such as coupled systems. I quickly realized that no single tool covers all necessary domains, so which are thermal hydraulic models, models for the electric network, but also models for advanced control, like model predictive control, for example. You can now use co-simulation, which is a really nice solution to this problem because it allows to cherry pick tools that are specifically targeting each of these domains, and you can couple those tools and models. I, for my work, rely on the functional mockup interface specification, which is basically a standard to link models and simulators. At the moment, more than 100 tools are already supported for the FMI standard. And at AIT, we also developed interfaces for additional tools like Python, Power Factory, Panda Power, etc. So when I started with developing the method, I wanted to have a model for the physical system, basically representing the electric distribution network and also the district heating network explicitly, and couple those physical system models with different control system models that might be rule-based, that might be optimal control that might be supervisory, can be central or distributed controllers, or any mix between those. So the method I came up with is a method that uses a dynamic model for the district heating network using Modelica. I developed an open source Modelica library for district heating networks, which is based on the open source ePIPSA library. So this model relies on transient thermal models and a quasi-static hydraulic approach for the hydraulic problem. This district heating network model is then sequentially coupled with the electric distribution network model, where I use PandaPower, which is a Python-based open source package, and which I use to solve the power flow equations for the electric network at each time step. So this basically allows to assess effects on a time scale of several seconds to minutes in the electric domain. I then use feedback from this physical system, so from both the district heating network and the electric network, like measurements of temperatures in a tank or any other state of the physical system, and send it to the advanced control model, which uses this feedback to derive new, maybe optimal set points if you use model predictive control, for example, and send these set points then to the physical system model at each control time step. So this is repeated at each control time step. But let's have a look at an example. So we have here a network with 14 buildings. This is the district heating network. You see a screenshot of the Modelica model on the lower right. And we have here electric network with transformers, lines, PV generation, and electric load for each building. The building demand is here represented by time series. We have a detailed secondary side of the district heating network. For example, we have heat exchangers, valves, we have tanks, and for this example, we use electric booster heaters to prepare domestic hot water, for example. So the first use case for the method is to control the supply temperature of the main district heating supply unit. So we basically lower the supply temperature at this main supply unit and use the decentralized electric booster heaters to guarantee domestic hot water supply, so both comfort and to avoid Legionella. And we see that this method basically derives or allows us to assess very detailed network insights when it comes to temperatures supply temperature at the consumers, or differential pressure levels at each consumer, but also voltages at each consumer. On a higher level, we can assess different performance indicators. Basically, we see here that, for example, pump energy increases when lowering the supply temperature. We see that district heating losses decrease, and we also see that power imports increase, for example. Another, maybe a little smarter application for the method is to control these decentral electric booster heaters with model predictive control. So now each of these electric booster heaters has model predictive control that controls the electric heating rod. The goal of the MPC is to avoid simultaneous use of domestic hot water and space heating to lower the peak generation of heat of the main district heating supply unit. On the other hand, we can use the electric heating rod as a flexibility option for the electric network to, for example, increase the self-consumption of PV generation. And we can now compare the model predictive control algorithm with other controllers, like a simple control that is only using PID controllers. We can also assess the impact of different forecasting methods, like using perfect forecasts or simple naive forecasts, where we use the demand of the last 24 hours, for example. And we see that PV self-consumption is increased by using the MPC. We can also see that the heat demand of the district heating network is decreased. So in summary, to conclude my work, this method is can be used very versatile. So basically you can do control assessments. We can also validate different designs, like using a larger storage tank. The method can also be at the core of digital twinning use case. We can do what-if analysis. So what if we replace the electric heating rod with a heat pump, for example? And even better, we can use the method to understand and also play around with these complex systems to have better insights into how these coupled and multi-energy networks work. So thanks a lot for your attention. I also want to point at the resources that I used for and developed for this work. So most of the resources and models are, so all of the models are open source. The only resource that is proprietary is Daimler, which, yeah, unfortunately is quite expensive, but yeah, that's the only downside. So thank you for your attention. I'm happy to answer any questions.
All right, yeah, thank you very much, Benedict, for your short presentation on your future-orientated topic. So I think this coupling of sectors will become essential for our sector in the future. So thank you very much for this excellent contribution, and congratulations to the first prize. So now we have time to ask some questions. We're starting a question and answer section. So, and I would like to all the winners to share your screens so that we can make like a round table conversation, and I will have a look at the chat about the questions that already arise, and maybe some more are coming. Okay, we start with a question to Martina. Martina, you were looking very much on the optimization of our district heating system and focused on this demand side and production optimization. And one question that appeared here from the auditors was, how is the electricity network integrated with the thermal networks in your model, or is it integrated? In future work, could you integrate electric vehicles, batteries, or other sources? Microphone, you have to switch on.
Sorry.
No problem.
So thank you for the question. Well, since we did not modify the electric load at the plant level, it was known from the beginning. So there was no need to include the electricity network model in the optimization tool, as it happened, for example, for the thermal network. But this is a part of what could be done for future works, and of course, there also could be the possibility to integrate electric vehicles, batteries, and other sources.
Okay, yeah, but this question came before the presentation from Benedict, so I will ask you this, or give you the possibility also to answer about this question, how about integrating electric vehicles, batteries? Is that part of your model already, or are you just taking the electricity grid?
So in my work, I really concentrated on the coupling between the district heating and the electric network, which does not mean that the method is not or usable to also integrate electric vehicles. So basically, that would be easily possible as an additional flexibility option for another model predictive control or the same home energy management system or whatever. So I don't see any problem to integrate any other electric load.
Okay, good. So it's only a question of time and how much effort you put in expanding the model. Question to Antoine. You were looking especially on the situation in France, if I understand correctly, and the malfunction of substations in some district heating systems that you looked at. What is your idea or your understanding? How can these results that you presented can be transferred to other countries? Is this situation special in France, or are there similarities?
No, I think the situation is not special to France. All the data I've got from about the malfunction statistics come from Nordic country, from Denmark or Sweden. So in France, it's the same situation because I saw on the field the state of the district heating, but I think it's everything the same in all the country.
Okay, good. So whoever has need in optimizing substations can address you.
Yes.
So then the next question is from the question box. It goes to Benedict. How did you calculate the building thermal demand? Are the buildings modeled with a physics-based approach?
Mm-hmm. So for my approach, I use, as I think I presented it quickly, I use time series as input. But the nice thing with, so these time series are also generated with physics-based models, but I just don't dynamically evaluate those buildings every time I run the simulation, and it's easier or faster to use data files as input. But the nice thing with Modelica or even with co-simulation is that you could easily integrate dynamic building models. So, for example, using Energy Plus or Modelica itself to model the building thermal demand in detail and also control it.
Okay, so but this would be an additional package. So as I understood, in your work, you used the data of the buildings that were available for the network that you were looking at. So the heat demand of the buildings was given and was not changed for this.
Exactly. I mean, I tried around with dynamic building models also, but I have to admit I'm not an expert on modeling buildings, which is also quite a complex task. I have colleagues that do that full time, so I would go to them and ask them for a dynamic model of a building and integrate it in my co-simulation approach.
Okay, perfect. Thank you. Martina, I have a question to you about the demand side management. As I understood, you were looking on the one hand on the production facilities, on the power plants, and you were also looking on the demand side, on the customer side. Yeah. So how would the customers respond to your demand to change or to adapt their demands to the needs of the system? Do you have a feeling on that, how customers would react on demand management?
Yeah, actually, these demand-side management strategies have been tested in some cases for test simulations. Well, I mean, in real cases, but by means of agreement with the customers is supposed to be possible even on a larger scale than the test that we have conducted together with the society that is managing the district heating network of Turin, for example.
Okay, yeah. And thank you. Yeah. So question, I have another question for Antoine. So regarding the impact, as I said, one of the criteria that we used when evaluating the papers was the impact on the market. What is your feeling? How would the results of your work impact the market, and what is necessary to do in order to reach a real good impact?
Yeah, in fact, the main problem is to have enough data to use indicators in order to analyze the district heating system, to show where is the non-optimal point, etc. And if we correct the malfunction, you will end reducing and increase the share of renewable energy, so decrease the price of the district heating system. It will be a great thing to develop in France, of course, and in the world, the district heating system.
Okay, and an additional question: you will, as I understood, you have the mass flow. The mass flow is your parameter that you are measuring. Is the idea that these algorithms of control are implemented in the substation controller, like an intelligent agent that identifies the key figure, or is it more the idea that this data is transferred to the district heating operator and he analyzes these mass flow data by routine?
Yeah, for now the idea is to just to provide tools, very easy tools for the operators. So just they have to see some alarms if a result is exceeded. There is an alarm with ringing, so they can see very fastly where is the problem. I think the next step is to implement it directly to the substation. But for now, there is a need for the operator to analyze a little bit the data. For now.
Okay, great. So looking a little bit at the time, we have a few minutes for questions from the audience. And one is here for Benedict. Were there any cooling demands connected to the network? If so, how was your strategy to balance heating and cooling loads?
So for the moment, or for the applications I presented, there were no cooling demands integrated. So basically my work really concentrated on methods development. But again, the nice thing is that you can use basically the same models that you use for district heating also for district cooling. And the tough question then is how to control your demand and your different assets like heat pumps, etc., for cooling and heating. But I did not have a more detailed look on this question. No.
Okay.
But I see it as a really important application for the future, of course.
Okay, as we are here in some kind of networking group and want to establish cooperations, I would like to ask all the three of you, what kind of cooperation are you looking for? Who could help you, who could help you in continuing your work, your research? What kind of cooperation partners are you looking for? Martina first.
Well, I am open to collaboration for universities and also industries that can helped me to expand my work and also to apply it to real cases.
Mm-hmm. So real cases to validate the method.
Yeah.
Good. And Antoine, how is it for you? What kind of cooperation are you looking for?
So I'm looking for the distributing operators because I need the data also and the feedback and about the indicators or about what is the malfunctions they see the most, etc., etc. For now, I don't have any data on this, so for France, in fact. So,
okay.
Yes.
Good. So all the district heating operators listening today, they have to. They should address you. And Benedict, what is your favorite cooperation in the network? For the future?
I think a nice thing would be to basically be part of developing a city district or a quarter, and be part of the decision making there and also assist in technical questions. So that would be really interesting.
So to enlarge the model to real systems. Okay, good. So I think this message was heard by everybody. And the final question again to all of you, what our participants are interested in is, what is your near future? So what is the near future of our winners? What are your plans on the scientific or also on the private sector, the fields? Yeah, we do the same order. Maybe Martina first.
Well, I'm just at the first year of my PhD, so I'm going to continue with my PhD and to move on with my research in the next few years.
Good. And Antoine, what are your plans?
Yes. For me, it's my last year in my PhD, so I am writing my thesis right now. So I want to defend in October, I hope. So
okay,
the next future.
So and afterwards,
are you afterwards, open? Sorry.
Are you interested to go into the industry or stay in the research field sector?
I think stay in the academic research and give lectures to students that are actually doing that. So I will continue next year, I think.
Perfect. So Benedict, I know that you are pretty much at the end of your PhD,
yes.
So that's quite interesting. What are your plans?
So for the moment, I'm on paternity leave and hopefully finishing my PhD during that time also and handing it in, finishing my last paper. And yeah, afterwards I'm already working as a scientist at AIT. So I think I'll stay there for a bit longer.
Okay, great. Thank you very much to all of you. So basically the three are open for cooperation. So this addresses now our participants, whoever is interested to cooperate and to learn more about this research, feel free to contact either the DHC Plus platform. We can give the contacts, or you can also contact the reference directly. So now we come to the prize ceremony. So normally we are now standing on the podium and giving the certificates. So we have to do it on a virtual basis now. So the first place again to Benedict Leitner from AIT, Austrian Institute of Technology, in cooperation with the TU Vienna. Congratulations to you, to the first place. Second place, Antoine Fabre from Mines Paris Tech from France. And third to Martina Kapuna from Italy. So the prizes for the three of you is a research contribution of 1,000 euro for the first place. And for all the three of you, an article to be published in the Euroheat and Power magazine. And this is interesting for all the participants. So the papers that were written are published in issue 3 and issue 4 in 2020. So this will be the next editions or the next issues of the Euroheat and Power magazine. There you can read all the details on the work. And as an additional prize for the 3 of you is the invitation to participate in this year's DHC Plus Summer School, which will be held from 23rd to 29th of August. And yeah, so this is your prize. You can choose if you have time in August to participate in this international summer school. So again, congratulations from DHC Plus and all the sponsors who made this student award available. They are named here, the IEA DHC Plus CHP collaboration, and thanks to Energyville who were sponsoring these prizes. Thank you. So now to finish up today's webinar, I want to make a little bit marketing for the DHC Summer School, which is the second main activity in the education and training pillar of DHC Plus. And the summer school takes place since 2013. There was the first summer school in Berlin. And every year we meet in different locations, different countries to exchange the latest research and the fundamentals of district heating and cooling with young researchers and students. And now this year we have this dilemma that we cannot meet. Summer schools normally live from meeting and be present and networking, but we found a very nice and interesting format to continue this series of summer schools. And so the 8th International DHC Plus Summer School will be held online. It has a focus on digitalization in the district heating sector. And everybody who is interested and has not signed or registered for the summer school is welcome to do so. And as I learned from Oksana recently, it's very the interest is very high to this online version. So we only have 6 places left, and so everybody who is interested to join us and to meet experts from the sector again in August is welcome to register for the summer school. And I hope that I will see the 3 of you there in some kind of format. If you can make it available, it would be a pleasure for me. Okay, so now we are at the end of today's webinar. I thank all of you for participating. We have still 19 participants, so thank you very much also for asking the questions and following the discussions. Thank you, everybody. Have a nice day, stay healthy, and connect again soon with DHC Plus. Bye-bye.